would be the real nuts and bolts of fibre itself, difference between single mode, multi-mode fibre, talking about connectors and different wavelengths and so forth. We're then going to move on to improving our network performance. So we're going to be looking at the importance of inspecting before connecting and cleanliness on connector interfaces and so forth. We'll then talk about some common tooling you'll come across for fibre testing. So your visual fault locator, light source and power meter, optic loss test set. And then we're going to go into a bit of a deeper dive into OTDRs. So that's probably going to be about 20 or 25 minutes of the presentation is just talking about OTDRs, theory behind operation, how they work, and then we'll obviously run through using and configuring an OTDR to get the best results out in the field. So starting off, just a bit of an introduction to fibre. So why fibre? Well, we're seeing more and more fibre, or fibre become more and more prevalent in the communications industry. It's moving from something that was typically found in the backhaul of and core of networks, moving right out to the edge. We're seeing that with a lot of rollout of 5G, where fibre is literally going as far to the edge as possible with fibre to the antenna, and we're seeing really new technologies associated with that, with RF over fibre and so forth. So fibre has a lot of benefits that I guess it overcomes downfalls of traditional legacy copper technology, whereby fibre has a much better performance in transmitting information over longer distances. It also doesn't suffer from some of the weaknesses, such as getting interference from electromagnetic fields or perhaps lightning strikes, which is obviously, once again, very relevant as we see more and more fibre being used in cell sites and up cell towers and so forth. So let's have a chat about, I guess, starting at the ground floor. Essentially, what's the difference between the two main types of fibre? So single mode and multi-mode fibre are the two types of fibre you'll find. The main difference between the fibres itself are essentially structured the same, with the main difference between the two being the actual core diameter of the glass itself on the inside of the fibre. So we can see that multi-mode fibre has a much greater core diameter than its single mode counterpart. So what's the benefits or pros and cons of each of the single mode and multi-mode? Well, single mode has much better performance when we talk about being able to transmit light over longer distances. So it's got a much lower attenuation than multi-mode fibre. So I guess, why would anyone go with multi-mode fibre then? Well, traditionally multi-mode fibre was a lot cheaper to manufacture, and the supporting infrastructure components were also a lot cheaper. So that made it really good for applications where distance of transmission wasn't really a factor. So we're talking inside data centers, inside local networks that were reasonably short. Now, with obviously the cost of manufacture of single mode fibre and associated infrastructure and components coming down as well, we're seeing more and more applications that were traditionally designed or targeted towards multi-mode fibre moving across to single mode fibre, because it doesn't have that cost downfall with it. When we talk about attenuation, as I mentioned in the last slide, what we're talking about there is if you've got a clean, straight piece of fibre, no faults or issues on that fibre at all, it's brand new, absolutely 100% good to go, we're still going to have some degree of light loss as light passes from one end to the other end of that fibre. So we can see that for multi-mode fibre at 850 nanometers, typically you're going to see about 3 dB of light lost per kilometre. And in comparison to single mode at 1310, you're only at 0.3 dB. So this really highlights the fact how single mode is a much better fibre type for being able to transmit that light over much longer distances. When we talk in terms of acceptable standards, the typical standard for multi-mode fibre is 3.5 dB per kilometre, and single mode is 1 dB per kilometre. Now, this is important to remember when we start talking about configuring our OTDR for acceptable pass and fail standards later on in the presentation. But just know that these standards, whilst they're typical, you also need to consult, your own customers' network performance standards that they might have. So they might have stricter or more tight tolerance standards than than these standard, I guess, regulations. In terms of wavelengths available for transmission across fibre, typically all your networks will be operating at somewhere between 800 nanometers and 1600 nanometers. There's also then a second band between 1625 and 1650 nanometers, which is specifically allocated for maintenance purposes. So for the 800 to 1600 nanometer band, I've sort of got a bit of a graph here on the right-hand side, which shows the attenuation rates against specific wavelengths. So we can see that for our multi-mode wavelengths, we've got a much higher attenuation rate, and that obviously coincides with what I mentioned in the last two slides, where it's not as good as being transmitted over longer distances, whereas the single mode wavelengths, which have a much lower attenuation rate, are ideal for going over that longer distances. Just on this graph here, you also notice these two absorption or water peaks. So these were traditionally, I guess, faults with older types of fiber or fiber that wasn't manufactured recently, where essentially water particulates in the fiber would create high attenuation levels at wavelengths in these areas. So with new manufacturing techniques of fiber, essentially these water peaks have more or less disappeared from modern fiber, and as a result, we've actually got more essentially spectrum that we can effectively use, and we can see that on this lower water peak in sort of the 1200 nanometer wavelengths. That actually is primarily where C-band DWDM operates from memory, so that obviously gives a new piece of space that we can effectively use for transmission of data. When we talk about 1625 to 1650 nanometer, that maintenance band, what that enables is us to undertake testing on live networks with filtered test equipment, i.e. test equipment that filters out all other wavelengths without needing to then turn off a live network. So we can undertake testing without creating interference to other people or other users of that network, which is obviously ideal. You can imagine if a service provider had to turn off an entire street in order to undertake testing on the fiber network, that would obviously be a huge hindrance for a lot of people. So by using an allocated maintenance piece of the spectrum with associated filtered test equipment, we can actually enable maintenance on live networks. Next, we're just going to touch on connectors. So obviously, as I'm sure all of you are aware, there's a wide range of connectors out there that you'll see across fiber networks. The four main types you probably see is up here with SC, LC, FC, and ST. I'd say that SC and LC are probably the two main ones that you would see out of those four, though. It's absolutely paramount to understand that you only connect like connectors to like connectors. And when I talk about connecting like connectors to like connectors, I don't only mean LC to LC and SC to SC, but also making sure that the polish type is the same. And this is probably more important because if you try and connect a UPC or ultra polished connector to an APC or angled polished connector, what you're actually going to do is essentially damage both end faces. And when you damage both end faces, not only will that require replacement of both the male and female side, but if it goes unnoticed, you're actually going to have a very high loss event in your network, and that could lead to issues when you come to troubleshooting or when you come to using that network. You're going to lose a significant amount of light over that particular connector if it still works at all. So the entire link might be brought down by it.
About half a dB that you lose.
So, all right, so that's sort of, I guess, real basics of fiber networks. So I guess now we're going to be moving on to ways we can look at improving network performance. So for those of you who don't know, around about 80% of field test failures and troubleshooting on fiber networks is caused by dirty connector end faces, which is caused by dust, dirt, oil getting on the end face of your fiber, and essentially creating impedance to the light passing through that given fiber. So how are we going to overcome this? Well, we're following this procedure here of essentially inspecting before you connect. So in that procedure, whenever we want to connect two fibers together, or a fiber to a patch panel, maybe a launch lead to your OTDR, whatever it might be, it's absolutely paramount that you inspect both the male and female side before you connect. So we take a fiber inspection probe, which I'll talk about shortly. We want to inspect the fiber end faces and ask ourselves, is it clean? If it's clean, fantastic, we can go ahead and connect. If it's not clean and we've got a dirty fiber end face, we need to use an appropriate cleaning technique or tool in order to clean that end face, at which point we will re-inspect it, ask ourselves, is it clean again? Hopefully it is, and then we can connect it. If after multiple cleans, the end face still isn't clean or the dirt still isn't removed, what's probably occurred is that someone has connected a dirty connector together previously, and that dirt has actually led to scratching and pitting on the end face. At that point, the only way to rectify that fault is through a replacement of that given connector. And obviously that's going to lead to an increase in cost and time spent on maintenance, which obviously is not ideal. So having a different look at a dirty connector end face, here we've got two connectors coming together with dirt trapped in between. And we can see that the light passing from left to right, as it reaches the dirt, is obviously going to have trouble passing through it. And we can see that the light moving into the fiber on the right-hand side is significantly weaker than that coming from the left. What does this mean? Well, if we have multiple dirty connectors in a row, that light may eventually not be able to make it past that next dirty connector, and essentially that whole link is going to come down. Additionally, if we have a really long link, say 30, 40 kilometers longer, a dirty connector at the start may mean that the light is sufficiently weakened that it won't actually make it to the end of the link as well. So there's two really big issues there that can be attributed to dirty connectors beyond creating that physical or permanent damage to those connector end faces. So how are we going to overcome this? Well, we want to obviously clean the connector end faces, and there's a lot of solutions out there, whether it's disposable solutions like this or reusable essentially kit or tool that you can purchase where you just simply top it up with cleaning fluid. The two main solutions, and probably the preferred one, is this one-click cleaning pen. Essentially, this works simply by connecting it to your patch lead end face or your patch panel port and simply clicking it, and it'll use typically alcohol in order to clean the end face of a particular fiber. Obviously, you can remove this little plastic end tip to switch between cleaning male and female connectors. On the other hand, you can use a cleaning cassette or something similar to this in order to clean patch leads. And simply it works by pulling the orange tab, exposing a new piece of cleaning fabric. You would then rub the connector in one direction only in small parallel lines in order to clean the end face. Obviously, once you've cleaned one connector, you release the orange tab, and if you pull it again, you expose a clean piece of cleaning fabric. So each of these are very cheap solutions. You know, you're going to get 800 to 900 cleans out of each of them, and it can lead to a significant improvement in network performance. Not only significant, in addition to significantly reducing the damage that can be caused to your network from those dirty connectors and so forth. So, you know, whilst it's a small investment in a consumable product, it can save you a huge amount of money and time later on. If you're going to, you know, could save you damage to your OTDR, which could be hundreds of dollars to get repaired, as a real quick example. So when we talk about dirty connector end faces, what are we looking at? Well, a dirty connector end face, a prime example would probably be on the left here, and this is not uncommon. So this would be a great example of this would be you have a launch lead in your toolkit and it's been, you know, rolling around in the bottom of your toolkit or in the back of your van for a while, and the plastic end cap hasn't been on. All of a sudden, you've got dirt and grime and dust on the end face of your fiber. Additionally, you could have a patch lead hanging in a patch panel. For whatever reason, it hasn't been connected, and once again, without that little plastic cap on the end, and it's just been exposed to dust and dirt over time, and obviously it's just built up. In comparison, on the right-hand side, we've got an example here of a correctly cleaned and polished fiber end face, and we can see the difference that cleaning makes, and we can see that there's absolutely no dirt on the end face at all, especially, and the part that we're especially concerned about is this core of the fiber here. So we can see that there's dirt on the actual core itself, which is going to have the greatest impact, but we essentially want an entirely clean fiber end face to make sure that we've got that good mating between two connectors as well. We've got some examples here of connector end faces that are being cleaned poorly or using the incorrect techniques. So we've got that first one where someone's tried to wipe the fiber end face on a shirt, and not only is that, you know, introduced, you know, maybe sweat or oil from their shirt as well, which has been wiped across the end face. But if there was dirt or dust on that end face, they could have also scratched the end face, which will lead to permanent damage, and as mentioned, would need actual physical replacement of that connector. The bottom two are interesting. So what we've got here is this first example is a prime example of why we need to inspect both the male and female side of a connector. So we can see that in this instance, someone has cleaned the female side of the connector, but then they've gone and connected a dirty patch cord or patch lead, and as a result, that's introduced new dirt and grime onto the end face. So, you know, they've only sort of done half the procedure, and as a result, we can see that, you know, it's introduced dirt, which is obviously going to, once again, impede light passing through that connector and could lead to physical damage. Finally, we've got someone here who's actually cleaned the connector end face correctly, and then we've gone and re-inspected it after cleaning. And this highlights why we need to inspect after we clean, because the cleaning pen itself has leaked alcohol residue or it's released too much, and as a result, it's dried across the fiber interface, and once again is bringing in a new contaminant to that interface. So how are we actually carrying out this inspection of these fiber interfaces? Well, typically it's done through using fiber inspection probes, and there's a whole different range that will change depending on your application you're using for, and you need to find one that'll best meet your needs as well, because if you start using inappropriate tooling, then that obviously leads to technicians and tradesmen getting frustrated with it, or they're not using the proper techniques and essentially blowing it off. So for small applications or jobs where you don't need to inspect as many fibers, then probably something like the P5000i is great. It's auto centering manual focus probe, so it probably takes 30 to 40 seconds to undertake an inspection depending on your particular skill level, and it works with a whole range of devices, whether you want to view it on your phone, on your OTDR, on your tablet, on your PC, whatever it may be. For people who have a lot more inspections to do, so maybe working in a data center environment, or you're undertaking work on a cable with 256 cores or something, maybe you want something like the FiberCheck probe, which is auto-focusing, auto-centering. You're looking at moving from 30 to 40 seconds per inspection down to 7 to 11 seconds, and it'll automatically give you a pass-fail indication. And then if you're working with MPOs, maybe you need to look at something like the Sidewinder, which will give you just more capability for undertaking those MPO connectors, automatic inspection procedures, and automatic focus for multiple fibers on an interface. So just a summary on fiber cleaning and inspecting. It's absolutely paramount that you inspect before you connect. And there's multiple reasons for that, as I mentioned. First and foremost is you want to maintain that good network performance. It reduces the amount of time you're going to spend troubleshooting brought about by dirty connectors. And you also want to prevent damage to not only your own test gear, but also the network itself, because that's going to lead to cost and time blowouts. Finally, you want to utilize a suitable inspection probe. And that's probably one of the most important things, because if you give your technicians the wrong gear, or if you're using the wrong gear, then you're going to get frustrated by it. You might start blowing off the inspections, and obviously that could come back to bite you in the future when you spend a lot more time troubleshooting or coming back to replace broken or unserviceable connectors. So there's some key things to consider. Okay, so moving on now, we're going to talk about some other fiber testing tools. And the main ones, as I mentioned earlier on, we're going to talk about quickly is your VFL, Visual Fault Locator, Light Source and Power Meter, Optic Loss Test Set, and then we're going to go a bit deeper into OTDRs as well. So VFL, so Visual Fault Locator, starting off. So think of this essentially as a red laser pen. So essentially it emits light at 650 nanometers, and it's used for two primary purposes. And the first one would be fiber identification. So an example of that would be you've got a patch panel in one room, maybe 10, 15 fibers running out of that patch panel, then up into a wall cavity or into a ceiling cavity, down a hallway and out into another patch panel in another room. To identify which fibers which between the rooms, you can connect your VFL on one end of a fiber, walk down to the other end of the fiber, and identify which fiber has that red light emitting from it. Remembering not to look down the fiber, shining it on your hand, on the wall, on a piece of paper to identify that the light's coming out of it. And then obviously connecting that to the appropriate port in the patch panel. A second use would probably be as shown in the image on the bottom right-hand side of the screen, where it's used as a very crude fiber, fault identification tool, where we can see when there's a physical break in the fiber, the red light is escaping. So we can actually see physical breaks in fibers. Now, the con of that is that you need to be able to see the entire length of fiber. So if we go back and talk about that situation where you've got the patch panels running into, the patch leads running into a wall cavity and down a hallway, you won't be able to see that fault if it's behind a wall cavity, which is obviously a significant downside. So pros and cons of the VFL, it's very cheap, it's very easy to use. Sort of like $100 would get you a VFL that's good for 5 kilometers. And the cons, well, you need to have access to the whole length of fiber if you want to be using it as a bit of a troubleshooting tool. Next solution up, would be your light source and power meter. So your light source and power meter are essentially used together as a pair. All your light source does is, depending on which model you purchase, is it emits light of a particular wavelength. at a particular power level. Your power meter, on the other hand, all it does is detect light coming into the power meter and will give you a reading for the power level of that light. So that's all that each of those two devices do, and together they essentially are used to check the continuity of a piece of fiber. So how would you use this in the field? Well, you'd have both units next to each other at the start, and you use a patch lead, maybe 1 to 2 meters, to connect the two and test, do a rough sort of field calibration to make sure that essentially at the start, when in such a short piece of fiber, there's essentially 0 dB of light loss between the two. So that means you've got a good reference point to know that when you go and test your fiber in the field, that you've got an accurate test set. Next, once you've done that rough sort of field calibration, you'd go connect your light source at one end of the fiber, turn it on, walk down to the other end of the fiber, connect your power meter and get a reading for the light lost across that particular link. Remembering that your light source and power meter, or your power meter in this instance, won't tell you if there's any faults in the fiber. All it will tell you is how much light is lost across that link. So it's then up to you as the technician or the engineer to interpret that result and determine if it's a pass or if it's a fail, or if there's potentially faults with that given link. So it won't actually tell you if there's a fault, and it won't tell you where there's a fault. So hypothetically, if you've got a 100-meter long link and you identify that there's 10 dB of light loss, you need to understand that that's unserviceable and that you need to invest in more troubleshooting in order to find that possible cause of that fault. Likewise, if you've got a 10 or 15 kilometer link and there's only 3 dB of light loss, once again, you need to determine if that's a serviceable limit that you'd be happy signing off on. So the pros and cons of light source and power meter. Pros, it's relatively cheap. So once again, you could probably look at getting a light source and power meter pair for around about $1,000 and moving up depending on the extra sort of features you want to get with it. The cons, as I mentioned, it doesn't identify the location of the fault. It won't tell you if there is a fault. It's up to you to determine that. And another con is you need to access both ends of the fiber. So whilst that's not too much of an issue, if you've got a, say, 100-meter long piece of fiber, when you start talking about a 10-kilometer piece of fiber, 20-kilometer piece of fiber, obviously getting to both ends of the fiber adds serious time constraints, and especially with a light source and power meter where you need to be actively changing perhaps the wavelengths at either end or configuring the test sets at either end, that can add considerable amount of time. Okay, so the next one we're looking at is an optic loss test set. So an optic loss test set, essentially, its key features is that it enables bidirectional testing of fiber. And you can think of each individual unit in an optic loss test set, so each individual unit, as essentially a light source and power meter combined in the one unit. So where would you use this in comparison to a light source and power meter? Well, let's say that you're working in an apartment building and you've got a patch panel in the basement and a patch panel on the top floor that you want to test some fibers between the two. You could go up to the top floor, set up your optic loss test set on the fibers you want to undertake testing on. Then you can go down into the basement at the bottom patch panel. You can undertake all your testing from one optic loss test set, controlling the wavelengths, whatever tests you might want to do, identifying if the fiber's passing or failing, changing configuration settings and so forth, all from the one end. And then once you finish the test, you get a pass, then you can obviously just go back up to the top floor, collect your remote unit, and then obviously your job will be complete. If that was a light source and power meter scenario, every time you wanted to take a measurement, you would then need to go up to the top floor to read the power meter, maybe reset up your light source in order to trace it back down to the basement. So we can see that there's a huge time saving when you start talking about bidirectional testing and also being able to control both test sets from the one end. So pros and cons of the optic loss test set. Well, key pro is that you've got that bidirectional testing capability. You can also talk about configuring pass-fail indications, which means that you're going to start reducing human error. So you could configure the pass-fail settings in an optic loss test set before you go out in the field, or configure it in the office and then give it to perhaps a newer technician, and you know that they've only got to interpret a clear pass-fail indication rather than interpreting those results like you would with a light source and power meter. And also by having bidirectional testing capability, you're increasing the speed of testing significantly. So you get some time savings there as well. Once again, the cons, you're not able to identify the location of a fault. So whilst you get a pass and fail indication, if it's configured properly, you're not actually finding out where a fault in that fiber is. And finally, you also still need to access both ends of the fiber. So whilst it's not too bad over those shorter links, once again, if you start talking about 10, 20 kilometer long links of fiber, it can become quite a pain to be at both ends. So that talks about, so that covers all the basic sort of test equipment. Now we're sort of going to spend quite a significant amount of time having a chat about OTDRs. The first thing we want to understand is that OTDRs come in many different form factors with a whole range of options, depending on your specific application. So you want to make sure that if you're looking at one, you get one that sort of fits your requirements. So the first things we can look at is starting to combine OTDRs with these tools that we just previously chatted about. So visual fault locators, power meters, you can look at combining those together into your into one unit, which obviously will help with reducing the number of test sets you need to carry around, and can also lead to benefits through reduction in capital expenditure costs. So other capabilities you might want to look at is bidirectional OTDR capability. So this could include loopback options, so whether hard loopback with a piece of fiber on the far end, or having two OTDRs working together, essentially talking to each other. You can look at inspection probe capability, so combining it with those inspection probes that we talked about earlier as well. Do you need remote control? Do you want to be able to control it from your phone? So if you're doing a really long link, you can set up your OTDR at one end, secure comms room, drive out to where you're undertaking your repair in the field, repair it in the field, and rather than having to drive back to the end of the fiber, you can just pull out your phone, control your OTDR, see if that splice or repair that you've done is good to go, and then once it's serviceable, then you can leave the site as opposed to having to drive to and from the end of the fiber continually. Then obviously we can talk about combining with other features. So Ethernet and network testing capabilities are becoming quite a popular one for 100 gig and 400 gig solutions. So once again, depending on your requirement and what you need to get out of your test set. When we start talking about OTDRs and choosing not only an OTDR for a particular job, but perhaps one you're looking at buying, there's a few key things we need to look at to make sure that you get the right test set for the job. First and foremost would be your wavelengths you need. So are you looking at testing single mode fibers? Are you looking at testing multi-mode? Are you going to be undertaking testing on live networks? Do we need to discuss maybe filtered 1625 or filtered 1650 nanometer wavelengths? So remember that, so that will enable you to test on live networks without interfering with users of that network. We're going to talk about dynamic range shortly, but essentially dynamic range is how sensitive your OTDR is to light. And very crudely, there is issues with saying this, but it's essentially how far you can shoot a trace with your OTDR. And I'll clarify that shortly when I talk about dynamic range. Obviously, there's budgetary constraints. I mean, you can look at options anywhere from sort of $3,000 or $4,000 up to $30,000 or $40,000 more, depending on the sort of capabilities you want. So making sure you get something that falls in the right range for your solution and budgetary requirements is key. And then what additional options do you require, as we discussed on the previous slide. So let's have a chat about principles of OTDR operation. And we get a lot of confusion sometimes from even users in the field on how OTDRs operate. And by understanding essentially how an OTDR works, it will really help you when it comes time to troubleshoot in the field, or if you're having issues with your OTDR or testing on a particular link because you can't see a particular event or there's a particular fault occurring. So the key thing that you're going to notice compared to other pieces of test equipment is that an OTDR, you only need to connect it to one end of the fiber as opposed to both ends, as say with your light source power meter or optic loss test set. So here we've got our OTDR connected at one end of our fiber. We've then got what's called a launch cable or a launch lead. I'll chat about what that's used for shortly. We've then got our cable under test. So this is the actual fiber that we're concerned about testing. And then we've got our receive cable or tail lead on the far end as well. And so the first and foremost, the receive cable and launch cable, they're tools that we carry with us and should always be used when you're testing with an OTDR. They're identical, so they're just maybe a 150 meter piece of fiber, and it's essentially used to, on the launch cable side, remove the OTDR dead zone, which we'll talk about in the next slide, and our receive cable is used so we can test the serviceability of that final connector. So in the fiber under test, we've got some connectors, we've got a splice that we've undertaken, then we've got two connectors on the far end as well. When we start our OTDR trace and hit run, what happens is a pulse of light is emitted from our OTDR, and that pulse of light will be configured depending on how we've set up our OTDR, which I'll talk about shortly as well. That pulse of light then makes its way down the fiber, and And at each connector or each event, so whether there's a connector, a splice, a break, a bend, then there will be a portion of reflected light sent back to the OTDR. So now the OTDR will be able to interpret three things. The OTDR will know, first and foremost, how fast light moves through fiber. The OTDR will know how long that reflected portion of light has taken to go from the OTDR to the connector and back again. And it will also be able to detect how much light is returning to the OTDR. So with those three things, we're going to be able to use those three things, to determine a trace and how big this particular event was and how far away this particular event was from the OTDR. That first portion of light then continues down the fiber, and those reflected portions of light continue to return to the OTDR. So once we've got those pulses of light returning to the OTDR, this is essentially what's generated a trace. But the first thing we should understand is that whilst in that example, we showed one pulse of light moving down the fiber under test and those obviously returning portions of light coming back to the OTDR, a trace isn't determined by one pulse of light. It's done by sending out thousands and thousands of pulses of light, and those returning pulses and measurements are taken and averaged in order to generate this particular trace. And we can see that this trace lines up to this particular diagram, and we can see that at each connector, we've got what's known as a reflective event on our trace. So we can see that this reflective event is shown by a spike and then a small drop. And this small drop is the amount of light that is lost across a connector. So maybe that could be 1 dB, 2 dB, something like that. We then can see that each connector, we've got those reflective events, but have a look here. So we've got a splice here, and notice that there's no reflective peak at that splice. And that's because that's what's called a non-reflective event. So these spikes are shown by essentially increases in the power, and that's because it's reflecting a large amount of light back. And then we can see after that connector, because a significant amount of light was sent back, we've actually got a little bit of a loss as well. Now, typically splices are significantly smaller in terms of light loss than connectors, but in this example, for visual purposes, so we can actually see it, we've got a little bit of a dip here. Now, before I discussed OTDR dead zones and the use of a launch cable to alleviate that. So what is an OTDR dead zone? Well, when we start our trace with an OTDR, the pulse of light is emitted from the OTDR. And in that first X meters, and that distance will be dependent on the size of the pulse of light, the quality of the OTDR you're using, and so forth. So it might be 5 meters, might be 10 meters. The OTDR is not going to be able to identify faults and issues with the fiber in that first portion. And that's due to a couple of reasons, but primarily because there's such a huge amount of light being reflected back in those first few meters that the OTDR won't be able to identify any faults. Now, if we not use the launch cable and connected straight to the fiber under test, we're not going to be able to see that first connector or maybe second connector, depending on how close they are to the OTDR. So by using a launch cable, that's essentially a tool that we know is serviceable, and we don't really care about essentially testing. That means that dead zone falls on that launch cable, and that means that we'll be able to test the fiber under test from that very first connector, including the serviceability of that first connector. So we use a launch cable essentially to alleviate that OTDR dead zone. Now, event dead zones are the dead zones or the areas of the OTDR that the OTDR can't see immediately behind a given connector. And that'll be determined primarily by the pulse width of light that you use or you configure on your OTDR, which I'll talk about in the coming slides as well. So there might be, depending on the pulse width of light, there might be 20 centimeters behind a connector you can't see, or there might be 10 meters behind a connector that you can't see, depending on the size of that pulse of light. And finally, we use that receive cable on the far end of our fiber to enable us to check the serviceability of that last connector. All right, so moving forward, chatting about dynamic range. So I mentioned earlier that dynamic range can create a couple of areas of confusion for users of OTDRs. A lot of times people come to us and go, hey, we've got a fiber that's 100 kilometers long. What OTDR can you give us to enable testing on that? Well, the answer is not as clear cut as you might think. And obviously we want to give them a device that's going to guarantee the job, which means they need one with quite a high dynamic range. It's not as clear as answering how many kilometers can you shoot a trace. So the dynamic range is actually the parameter defining the maximum optical loss an OTDR can analyze from the backscattering of light. So in basic terms, it's how far an OTDR can shoot a trace, but there's a couple of issues with giving it a kilometer value. So to explain that, I'll sort of go through a few examples, and this is the first one. So we've got the same cable under test here as what we had in our previous situation. Now, though, we know we've got some additional information. So we've got an OTDR here with a dynamic range of 20 dB. The fiber under test, we can see that we've now got values added to each of the particular connectors. So 1 dB for each connector, 0.1 dB for the splice. And then remembering back to the second or third slide, I talked about attenuation rates of straight fiber. Well, here we've got 10 kilometers of fiber and we've got that 0.3 dB per kilometer of loss, which means for this 10 kilometer long link, we've got 3 dB of light loss total. So adding up all those incremental losses, we get a total loss over the entire 10 kilometer link of 8.1 dB. Now our OTDR has a 20 dB dynamic range. Because the dynamic range is greater than the total link loss, we're able to see that entire link of fiber and see it clearly. So we're going to get all the faults, all the events on that trace that we mentioned earlier, and we're going to get a good result and something that we can give to management or to our customer, and it's, you know, it'll be good to go. Let's have a look at another scenario though. So we've got the same OTDR, 20 dB dynamic range. We've got the same connectors under test, but now instead of a 10 kilometer long fiber, we're looking at a 70 kilometer long fiber. Once again, we've got that 0.3 dB of attenuation per kilometer. So we've got a total loss just on attenuation of 21 dB. This brings the total link loss to 26.1 dB, but we've only got a 20 dB OTDR. So what does that mean? Well, it means that we're not going to be able to see the entire fiber under test. So we'll be able to see essentially 20 dB of events, including the attenuation of the fiber, before that OTDR trace will essentially just fall into noise. So in this instance, that 20 dB might occur at maybe the 45 to 50 kilometer mark, which means that last, 20 odd kilometers of fiber, we're not going to be able to see, including these last two connectors. So if we wouldn't be able to submit a report to management or to our customer saying, hey, we've only tested the first 50 kilometers of fiber, that wouldn't be good enough. So in this instance, to fix that solution, we would need, say, an OTDR with a 30 dB dynamic range. That would bring the dynamic range up above the total link loss, and we would obviously be able to see the entire link again. But let's have a look at a different scenario. Now we are using that 30 dB dynamic range OTDR, and we have a link that is 30 kilometers shorter. So we've only got a 40 kilometer link now. But having a look at the connectors, we've now got all these connectors that are significantly worse than what they were previously. Not to mention we've got some additional damage from the guys that have hauled the fiber. Maybe they've put some zip ties around it and they shouldn't have crushed the fiber or something like that. So now we've got a significantly higher link with a significantly higher loss link with total dB of 37.5 dB worth of light lost. So now that even though we have a higher dynamic range OTDR on a shorter link, we still can't see the end of that fiber. So we can see how not only to test the whole fiber, not only do we need an OTDR with dynamic range high enough to get to the end of the fiber, but we also need a dynamic range high enough to see through the connectors and so forth on that fiber. So if you have a 100 kilometer long fiber with absolutely no faults at all, so no connectors, no splices, absolutely nothing, maybe you could see the end of it with a 20 dB dynamic range OTDR. But if you've got a 100 kilometer long fiber with 50 connectors on it, then obviously you're going to need a much higher performing OTDR to be able to see to the end of it. And this highlights as well the importance of what I talked about before with inspecting before you connect. If we bring each of these connectors down to 1 dB events through proper cleaning and inspecting, then obviously that can bring this total link loss down. We'll obviously have a higher performing link for the end user, but we'll also be able to test it easier with our OTDR as a great example. Okay, so we sort of talked about the theory behind OTDRs now, and now I just want to sort of, I guess, finish up by talking about how we actually run an OTDR trace. In this instance, I'm going to be running through on how to do it on a VIAVI MTS 2000 OTDR with a tri-wave OTDR module, so 13, 10, 15, 50, and 16, 25. If you guys aren't using this particular OTDR or a VIAVI branded OTDR, that's all fine. The theory behind what we'll be talking about will be the same across any OTDR. Maybe menus will be in slightly different locations, but the principles of what we will be discussing will be the same. If you are using a VIAVI OTDR, the user interface across your smart OTDR, MTS 2000, 4000, 5800, 6000, 8000, they're all the same. So you'll still find the settings and menus in the same locations. So when we turn our OTDR on, what we're going to notice first and foremost is the screen will be split into two halves. And the top half of the screen will be showing capabilities on the OTDR mainframe itself, whilst the bottom half of the screen will be showing the capabilities of that particular OTDR module. So for those of you who aren't familiar with VIAVI OTDRs, most of them have a mainframe and an interchangeable OTDR module. So if you want to switch between single mode testing and multi-mode testing, you can just switch the module on the back. You don't need to buy a whole new mainframe as an example. So we can see that up the top, we've got things like Smart Access Anywhere. So that's your remote control, Strata Sync for uploading files to the cloud, the Explorer setting, which could be where you're saving your previous OTDR traces. Now for today, we're going to focus on the bottom half. So we're going to be running through our OTDR traces in Expert OTDR mode. If you're a bit of a newer user, you're not too confident on running through in Expert mode, you can do what's called Smart Test. And this will be essentially a OTDR wizard. It will ask you, I think it's 3 questions. It'll ask you, what wavelengths do you want to test at? What report format do you want to generate? And what pulse width do you want to use? And that'll essentially be the main 3 questions it asks you, and then it'll run a trace and it will automate every other setting. It'll still give you a great result, but it might not have the exact configuration settings that your customer may need you to test to. So we're going to jump into Expert OTDR mode, and you can select that just by touching on the touch screen. When we click on Expert OTDR mode, this will be the screen that greets us. So the screen's broken up into 3 main areas. The first area will be, the trace view. If you turn your OTDR on like this will bring up the last trace that you've undertaken. If you're lucky enough to have a brand new OTDR, this particular screen will be blank. On the right-hand side, we've got a few of our settings. So in this view, we can switch between trace view, which is what we're seeing right now, and Smart Link Mapper, which essentially replaces the trace with small icons, making it much easier for users to view and interpret the results. And it's great for giving reports to management who may not have the skill set to read a traditional trace. We've also got settings to zoom and shift, so move the trace around, zoom in on the trace. We can turn on and off our cursor A and B, as well as move them from left to right as reference points. We've then got the fast report setting. So this is the button that we'll be pressing to automatically generate your PDF reports once you undertake a trace. Next one, we got manage projects. So this will let you then jump back in and see all the previous traces you've done on this particular cable. So if you've got a cable with 144 cores, you could be generating PDF reports for each individual fiber in that cable, but you may want to then get a summary of all of the cables combined, and you can view that through the manage project screen and see the previous traces that you've undertaken. And then we've got option for some advanced settings down there as well. This bottom portion of the screen is allocated to the actual event. So we can see each particular event is given a number along the bottom, and that coincides with each particular row in this table, obviously being able to scroll up and down. Now, the only difference between this view and views on larger model units, so like the 4000 or the 5800, is obviously we've got a bigger screen. You're going to be able to see more lines in this table down the bottom. For now, though, we want to set up a new trace, and we're going to do that by clicking the Setup Hard key on our MTS 2000. If you're using a fully touchscreen model like the 4000 or 5800, you'll have a soft key that you can press on the right-hand side of your screen for setup. So we click Setup, and we're brought into this screen here. So the first thing we're going to configure is our actual trace itself. So the first option is, do we want to do a point-to-point trace, or do we want to be working on are we working on a point-to-point network, or are we working on a PON, passive optical network? Now, the key difference between the two is that point-to-point is essentially one strand of fiber. A PON network will be testing where they're in a network where there's a lot of splitters, or there is a splitter. And the difference between the two in terms of the OTDR is that in a point-to-point, if you have point-to-point mode selected, and then your trace comes across a splitter, it's going to see that as a significantly higher loss event, and it's going to assume that that's the end of the fiber. Whereas if you select PON mode, it's going to get to a particular splitter. It'll see it as a high loss event, but it'll continue to try and run a trace beyond that splitter. Now, depending on which way you're trying to run a trace beyond that splitter, whether you're going towards the core of the network or from the core of the network out, will depend on how good a result you will get. And it also depend on if you're using things like reflectors and so forth. But we're not really going to touch on that today. We're going to be running through a point-to-point scenario. Next, we want to choose the wavelengths that we're using. So in this instance, 1550 selected. If we want to go by absolute best practices would dictate that you use the 2 wavelengths with the furthest or the greatest space between them, and that'll give us the greatest chance of enabling macro bend detection. So if you use one wavelength, you won't get any macro bends detected, but if you use 2 wavelengths, you will, and the further apart they are, the better. So 13, 10, 16, 25 would be ideal. Next, we talk about acquisition mode. So we're going through manual today, which enables you to choose the range, pulse, resolution settings. If you go into auto mode, it will automatically configure that for you based on how it sees how long the fiber is and so forth. And then we've got something here called smart acquisition mode. Now, smart acquisition mode would be something you would use on slightly longer fibers. And what it does is it combines shorter pulses with longer pulses. And I'll talk about the different pulses shortly, but that means that you'll get a higher resolution trace at the start of the fiber, and you'll still get good range. So you'll be able to still see events that are further down the fiber as well. So it combines short and long pulses together. Range, this only needs to be approximate. How long's the fiber you're under test? Now, notice all these are in feet. You can change these to meters in a menu coming up, which I'll show you where to do that. Pulse width. So pulse width is the next key thing. And I've chatted about pulse previously, but I guess this is where we really see the impact that it has on your trace. So the 2 things you want to consider is, 1, you want to use as small a pulse as possible, but you want to have the pulse be able to make it to the end of the fiber. So if the benefit of using a smaller pulse is you get a really high resolution trace, but the con or the downside of it is the smaller the pulse you use, the light simply isn't as powerful and it won't travel as far down the fiber. So if you've got a fiber that's, say, 300 meters long, maybe a 5 nanosecond pulse would be perfect for that. You'll get a real high resolution trace. The pulse will still be able to make it to the end of the fiber. If you've got a fiber that's 100 kilometers long and you use a 5 nanosecond pulse, you're probably only going to see the first 2 kilometers of fiber and then that's it. So you'll have to use, for a 100 kilometer long fiber, you probably have to start using, these 10 microseconds, 20 microsecond pulses to give that light enough power to actually make it to the end of the fiber. Now, when we talk about the pros and cons between those pulses, we can see that here we've got the same fiber under test, but the only thing we varied is the pulse widths. So here we've got the smallest pulse. So we've got a 10 nanosecond pulse. We can see that we've got the fiber under test. We've then got a connector, so it's a reflective event, and then we've got a little loss. And then we've got the rest of the fiber with a second connector here as well before it falls into the end of the fiber. Now we can see how high resolution that is with that small pulse. So that small pulse, we're able to see all the details. If 2 connectors are really close together, we'll be able to see that because we can see how precise that measurement is for that 10 nanosecond pulse there. We can then see as that pulse grows in size, we can see that we're starting to lose that real high resolution aspect of the trace. And we can see that when we get up to a 3 microsecond pulse, there's actually a significant area after that connector where we can't identify that there'd be faults. So as I mentioned before, that's that event dead zone where because the pulse is greater, we now have a greater event dead zone following a given event. And we can see that that's the same on all the events moving down the fiber. So we start losing those real high resolution or the ability to identify faults that are really close together. But if we're undertaking testing on a long fiber, we have to use those longer pulse widths to enable to get that details, all those faults at the far end of the fiber. So resolution, we're just talking about configuring how high resolution that particular trace is. Acquisition time. So we're talking about pulse widths, and we talked about earlier that an OTDR doesn't just send out one pulse, it averages lots of them in order to get a high resolution trace. Now we want to average as many as possible in order to get the high resolution trace, but we want to do it in a reasonable time frame as well because we don't want to spend all day testing. So if we're using something like a 5 nanosecond pulse over a reasonably short fiber, we could set it to 10-second acquisition time. Now that means that in a 5 nanosecond pulse, we'll be able to send out thousands and thousands of pulses over that 10 seconds. to get a real high quality trace. In comparison, if we had one of those 20 microsecond traces, if we use 10 seconds, we're not going to get anywhere near enough pulses of light down there to get a real good high resolution trace, and the overall quality of our trace will be quite poor. So generally, the higher the pulse, the larger the pulse size you use, then the higher the acquisition time you'll have to use in order to maintain getting that good trace. OTDR connector test. This is just enabling us to test the actual serviceability of the OTDR connector port itself. And you can choose not to do it. You can choose to do it and continue with the trace, or you can choose to test the serviceability and abort the trace. And why you would want to do that? Well, if you've got your acquisition time of 3 minutes for 3 wavelengths, that's going to be a 9-minute test. You don't want to spend 9 minutes waiting just to test the serviceability of the OTDR port. So in that instance, you tick yes and abort. And just here, we've on our launch cable menu, just notice that we've selected it to event 1. And what that means is that those launch cables and receive cables will show up on our OTDR trace. Okay, so next one down, alarm. So just quickly on the alarm one, this here is where we want to insert on our splice loss, connector loss, and slope are probably the 3 main configuration settings we want to adjust. And we want to do that and configure it to the acceptable pass and fail standards that for the network that you're working on. So your network will have given standards that of what a acceptable splice is, an acceptable connector is, and what our acceptable attenuation is. So once again, at the start of the presentation, I talked about attenuation of single mode fiber being 0.3 dB was typical. So here we've got a typical attenuation of 0.25 dB. So as that trace slopes down, that 0.25 dB is our acceptable standard. If anything's greater than that, we'll get a fail reading. Likewise, for our splices, if any splices above 0.1, we'll get a fail reading, and same with the connector for 0.5. Next, jumping down to analysis, the only real thing we need to be concerned about on this particular screen is the distance unit. So in this instance, it's in feet. You can click on that and change it to meters or kilometers if desired. This screen is probably the most important, especially if you're going to be using your automatic PDF report generator to submit to customers or management. So you can fill out or pre-populate all of this information. So your fiber ID, the particular fiber number you're working on, change fiber number. So when this particular setting has to do with your automatic report generation. There's 3 options here: no, increment, and decrement. So if you select no for your automatic PDF or automatic report generation, the fiber number or the fiber title will not change after each test. If you select increment, and in your file naming convention, you've got a fiber number identified. Every time you do a trace, it will count that fiber number up. So it'll go, whatever your naming convention is, fiber 1, and then naming convention on your next trace will be fiber 2, fiber 3, fiber 4, and so forth. So it'll count up. If you select decrement, it'll count down. So maybe if you've got 144 fibers, 144, 43, 42, and so forth. So why is that important? Well, you could have 2 guys working on a fiber, one guy starting at fiber 1, another guy starting at fiber 144, and you can work towards the middle. So you can both have all those reports with the same naming convention, and then you can submit them all to your management at a later time. Finally, continuing through with your cable ID, the direction you're testing from location A to location B, all of that information will be in your report at the end, along with your technician ID, all these engineering IDs, so who's done the job and so forth. And then you configure what number fiber you're starting at and how many number of fibers are in your particular cable. So this could be 144 or whatever it may be. And these are the numbers that you will be incrementing or decrementing up and down to match that all up with your report. Next one in your file, just where you're going to save the file and your file naming conventions. So this is where you can configure your automatic naming for your reports, and then down here, saving your report output, whatever you choose to. So you get an SOR file as standard, and then you can also choose for PDF output or a couple other file choices as well. And do we want to include our microscope images? So those video inspection probes we talked about before, do you want to include images from those in your report? Once we've done that, we're just going to hit start and stop to start our trace. First thing it's going to do is check the connection of your launch lead. And once it's done that, we're going to see that it's going to start doing the acquisition in process. So for our 5 nanosecond pulse, we can see that it's done 94,000 pulses of light going out in order to get this particular trace. Once we generate that trace, we can see, because we selected those launch cable settings, we can see that our launch cable is included on our trace and it's clearly identified adjacent to the end of the fiber. So that's great because now we know that this actual fiber under test is between event 1 and event 6. So it's very clear as to where our launch cable and receive cable are, and we know that they aren't part of the network under test. Now this traditional trace diagram can be a little bit confusing to some people. So what we can do is change it to Smart Link Mapper by clicking Smart Link Mapper option up here. And that changes it from the traditional trace view to getting this iconized view, or a view of icons instead. And we can see that our launch lead, the OTDR can identify where the launch lead ends, and the OTDR actually starts counting the distance of the fiber under test from your launch lead. So it understands that it's not going to include that 150 meters or 100 meter launch lead that you're using. We can see then along the fiber, we've got serviceable connectors and unserviceable connectors. And then we've obviously got our receive cable and our end of fiber. We can see that for this particular link at 1550 nanometers, we can see that it's failed. So we've got a failure here. And why is it failed? Well, there's 2 alarms or 2 faults, and they're both bad and dirty connectors. So once again, highlighting that importance of inspecting before we connect. We wouldn't have had a failed trace if we had inspected and connected these connectors properly. To click on each particular connector to get more details to find out about them, first of all, we can click on these serviceable ones and we can see that, hey, we've got those fail thresholds that we configured before as what passes and fails. We set it to 0.5, it's 0.315, serviceable, all good. Whereas if we click on the failed connector, we can see that same threshold is set, but now it's 0.575 for that connector, which is about 200 feet down the fiber. And we can see that it's failed, and it's because its reflectance and loss is too high, and it even told us that it's probably a bad or dirty connector. So we need to go back down the fiber, clean it and inspect it, and then rerun the trace. So once that particular trace is done, we might go, okay, we want to generate a report for our boss or for our management. So we click that fast report button, and out comes our PDF report. So this particular report was just a launch lead that we did in the office here in Sydney. So we can see that we've got our unit that we used with our information for what was put into that settings menu and that fiber and projects, that project window is pre-populated through here. We can see that we've got an icon of the Smart Link Mapper. Once again, because it's just a launch lead, there's only a start and end of fiber. In the fiber under trace, there could be 20 or 30 icons in this range, just to show a clear picture of all the events along the fiber. We get our traditional trace as well and a summary of all the events. If we tick that we want to include those microscope images as well, then they're populated as well, and we can see the fiber end faces on all of the given connectors that we may want to include in that particular link. And that sort of concludes this morning's webinar on introduction to fiber testing. I'm more than happy to answer any questions now if you had any. If not, feel free to send me an email or give me a ring. I'm more than happy to have a chat about any questions or concerns you may have. But other than that, thanks for your time.